Okay, thank you for that introduction. In this talk, I'm going to show you how we strengthen consistency while maintaining scalability and low latency for wide area storage systems. So when I talk about wide area storage, what am I talking about? I'm talking about the back end for huge websites, things like Facebook, Twitter, and Google+. I'm talking about storing everything you need to build those websites. So status updates, your comments, your friends list, these sorts of things. So why is this wide area storage? Well, if we take a look at the architecture of one of these sites, we'll see that we have many data centers in geographically distributed places. And what's one of the big reasons for doing that? It's so that clients can be directed to a nearby data center where we can serve all of their operations inside that data center and then return to them very quickly. So let's take a look at what happens inside one of these data centers. So as a client, when you connect to the service, you're going to be directed to a web server in a data center. So how does that web server actually build your page? Well, there's a thread of execution running on the web server that's going to read and write data from a separate storage tier. Now, as I mentioned before, we have multiple data centers here. So if you write anything into the storage tier, you have to replicate this out to those other remote data centers. So in this talk, we're going to talk about this storage tier, and in particular, how we can improve this replication. So when we started thinking about these sorts of systems, we wanted to define properties that we really wanted the storage system to have. And we call these the ALPS properties. So these include availability, which says that operations always complete successfully. Low latency, which says that operations always complete quickly, typically single-digit milliseconds. Partition tolerance, that says our system continues to operate even if we have a partition, for instance, separating the East Coast of the United States from Asia. And when you take these three things together, you get an always-on data store. Operations always complete, they're always successful, and they're always very fast. So in addition to these three properties, we also want scalability. So I want to talk about scalability in a little bit more depth. So what I mean by scalability is that we can increase the capacity and the throughput of the storage tier in each data center. So initially, if we have a small service, we can start with a single server in each data center. But as our site grows and our capacity and throughput requirements increase, we can add servers to each data center to meet those needs. Note that an important part of the scale-out property is that the parallel replication occurs across these data centers between servers storing the same portions of the data set, as shown by these parallel arrows. So in addition to these ALPS properties, we also want consistency. And so consistency is a bit more nuanced, but basically what it says is that there's some restriction on the ordering and sometimes the timing of operations that can occur. And we want to have the strongest consistency possible because this is going to make programming easier and it's going to make your user experience better. So what consistency can we achieve if we really want those ALPS properties? Well, let's look at the spectrum of consistency models and start with the strongest. So informally, this is called strong consistency, or more formally, linearizability. And what it says is there's a total order of all operations in the system, and that each operation appears to take effect between when it's invoked and when it returns. And so strong consistency is very useful, but unfortunately, it's provably impossible with the ALPS properties. Notably, the CAP theorem says you can't have strong consistency, availability, and partition tolerance. So if we move down the spectrum a little bit, we get to sequential consistency. And sequential consistency still gives us a total order of all operations, but it no longer includes that real-time requirement. And sequential consistency was the initial correctness condition for multiprocessors, and it's still very useful. But unfortunately, this is also provably incompatible with the ALPS properties. Notably, sequential consistency and low latency are impossible to achieve together in a wide area system. So if we can't have strong consistency, we can't have sequential consistency, what can we have? Well, if we take a look at some of the existing ALPS systems, these include things like Amazon's Dynamo, LinkedIn's Project Voldemort, and Facebook and now Apache's Cassandra system. You can configure these to give you that always-on scalable data store. But when you do this, you just get eventual consistency, which is this very weak property that doesn't really give you any ordering guarantees at all. So there's this general feeling that if I wanted this always-on scalable data store, I had to sacrifice consistency and settle for eventual. And so we're pushing on that in this work, and our system, COPS, sits in this white space here, in between the impossible to achieve sequential consistency and that doesn't give you very much eventual consistency. And what we provide you is something called causal consistency. And causal consistency gives you a partial order over operations so that clients only see operations in an order governed by potential causality. I'll explain that so it makes much more sense through an example in a moment. But first, I want to take the time to place COPS in the space of related work. So of course, there's this huge body of related work on distributed data stores. So I want to compare COPS to a few interesting points in that space. And that includes two presented in this conference, so Scatter and Walter. So both Scatter and Walter achieve stronger consistency properties than COPS, but neither of them achieve our desired ALPS properties. A much older system, Bayou, comes the closest, but it lacks COPS scalability because it only supports single server sites. And of course, as I've already said, there are existing ALPS systems like Dynamo, but these systems settled for eventual consistency. So we like to think that COPS inhabits the sweet spot here for achieving both the ALPS properties and providing a stronger form of consistency. So let's return to causality. What is this order that we're going to get? So I'll show this through an example. So I'm on a social networking website, and the first thing I'm going to do is remove my boss from my friends group. Then I'm going to post to my friends, hey, I'm looking for a new job. And then my friend Jeff will read this post. So we have 3 operations here. Where's the causality? I'll show it with some arrows. And there's 3 rules that define causality, and so I'll go through all 3 of them. So our first rule is the thread of execution rule. And this says that operations done by the same thread of execution, which in this example is me, are ordered by causality. So my first operation is before my second. Our next rule is the gets from rule. This says that operations that read a value are after those operations that wrote those values. So when Jeff reads my post, that read is after my write of the post. And then finally, we have the transitive closure of these things. So my first operation is still before Jeff's read of my post. So having operations show up in this causal order is very useful. So it's useful for you as a user because your operations appear in the order you expected. So I specifically removed my boss from my friends list so that my boss would not see that I want a new job. And it's also useful for you as a programmer because there's far fewer situations you have to deal with. So if I'm, in another example, if I upload a photo to the website and then I add it to the album, with causal consistency, I know that first operation will always show up first, so programmers don't have to deal with the weird situation of having a reference in an album to a picture that hasn't shown up yet. So causality is very useful, but there's this issue that comes up with causality, and that's that we can have conflicting operations. So what's a conflict? Well, we can have 2 people in different data centers in different places write to the same key at the same time. And so when these 2 people write to the same key at the same time, this is unordered by causality. And because it's unordered, we can have all kinds of strange things happen. So we can, in fact, have different data centers returning different divergent versions of this key forever. And so this is certainly not something that we want. Instead, we want all of our different data centers to agree on what the value is. And so one way to do this is to use the last writer wins rule. And this is the default policy in our system. And this is just to say, to arbitrarily pick one of the 2 conflicting operations and say that it's later, and then have it overwrite the other operation. And so we could do that with 2 here, and then each data center would end up with 2 as the value for the key. Now, of course, you can do things that are a bit fancier. For instance, you can use application-specific conflict handler functions. So we could do something like take the sum over these values and end up with 3 in each data center. In any case, what's important here is that all of the data centers converge on having the same value. So in this work, we introduced the name of and formally defined this combination of causal consistency and convergent conflict handling as causal plus consistency. So in fact, previous systems thought to provide causal consistency also provide this stronger property of causal plus consistency. However, as we'll see, they don't do so in a scalable fashion. So this previous work includes things like Bayou from the mid-90s and much more recently Practi, and they're all based on the same idea of exchanging logs of information. So when these systems were designed, they were thinking mainly of single machine replicas instead of our large data centers of many, many machines in each replica. And so what they do is incoming operations are logged to one point, and then you send these off to the other replicas, and those replicas play the logs in the order that was there. And so this is nice because you're implicitly capturing all the causality and then enforcing it when you play things in the order that they originally happened. But you have one of 2 problems here. Either you're limited in scalability because everything in a data center now has to be serialized in one point when you're logging it, and then even worse, has to be played from a single point when you're playing things from other data centers. Or if you partition your system and you separate these things out entirely, then you're not going to have any causality across servers. So what's our key idea that allows us to provide scalability and maintain causal consistency? Well, it's to move away from that implicit log-based approach to an explicit approach where we use dependency metadata to capture this causality. So we're going to get rid of that single serialization, and instead we're going to replace it with a bunch of distributed verifications. So we're actually not going to expose the value from replicated put operations until we've confirmed that all of the causally previous operations have already shown up in this data center. So now let's take a look at the actual design of our system. So COPS is organized as a geo-replicated system with a cluster of nodes in each data center, where each cluster stores all the data in the system. We use a scale-out architecture with many nodes inside each cluster, and we use consistent hashing to partition the key space across these nodes, though other centrally based approaches like those from XFS or GFS could be used here too. As we assume partitions do not occur inside a data center, we use strongly consistent replication for fault tolerance. Our current approach uses chain replication, though we could use other techniques like Paxos. Now, between data centers where latency is high and partitions may occur, we replicate data in a causal plus consistent fashion. Now, in addition to this key value store, we also have a client library that sits on our client. And this does two key things. First, it's going to track causality for us. And second, it's going to mediate access to the cluster in our local data center. And so by keeping all operations inside the local data center, this is how we provide our always-on data store. So let's take a look at how we actually do these get and put operations. So let's start with a get. So the client sends us a get, and the client library will send it out to the node in the local data center responsible for this particular key. That node will return right away, return the current value. The client library will update a little metadata, and then return it to the client. So what about puts? So the client will send us a put, and the client library will translate this into a put after operation. So a put after operation is like a regular put operation, except it's also going to include ordering metadata that says this value is only valid after that value shows up. We'll write the value right away in our local data center, queue it up for replication asynchronously, return to the client library, update metadata again, and return to the client. Meanwhile, the node in our local data center will replicate this out to our faraway remote data centers. But to see how we actually do that, I want to examine dependencies and understand what's going on with them a little more first. So as I mentioned, dependencies are these explicit pieces of metadata on values, and one of the main functions of our client library is to track them and then attach them to put after operation. So let's see how we do that. So here we have some client, client 1, and it already has a bunch of dependencies stored here in depths. So when the client sends us a put operation, we'll send this out as a put after and include all of our currently stored dependencies. The node in the local data center, when it returns, it'll include a version number. This version number uniquely identifies this value. Then we're going to insert the key version tuple into our dependency list. And we have to do this because of the threat of execution rule. So any future operations this client does are causally after this particular operation. So if any of those operations write a value, that value has to have a dependency on this value. And then finally, we'll return to the client. So let's see how get operations work. And we'll see this with a different client, client 2. So the client sends get operations to our client, sends the get operation to our client library. We'll send it out to the node in the local data center. And the node will return 3 things. The first is the current value for that key. The next is the version number that uniquely identifies that value. And then third are the dependencies that were initially written when that value was written. So now we have to update our dependencies again. We have to add a dependency on this particular version of this key because of the gets from rule. And we have to add dependencies on everything it depended on because of the transitivity rule. And then finally, we'll return the value to the client. So let's go back to replication. So you remember in our local data center, the operation comes in, we write it right away and queue it up for replication in the background. And when we replicate it in the background, we're going to send this key to the nodes in the remote data center that are responsible for this particular key, K. So now let's zoom in and see what's going to happen in one of these remote data centers. So this put after operation, this replicated put after operation comes in, and it has a bunch of dependencies with it. So the node's going to examine these dependencies and see, oh, okay, this has a dependency on key L version 337 and key M version 195. So it'll send out dependency check operations to the other nodes in the data center that are responsible for key L and key M. Those nodes will then check, have I already written this version? If they have, they'll return right away. If they haven't, they'll block until they do. Now, once all of these dependency check operations return to our initial node, it knows it can safely write the value because all causally preceding values have been written as well. So just to summarize this basic version of the system, we're going to serve all our operations locally and then replicate things in the background. So we get that always-on data store. We're going to partition our key space across many nodes to provide scalability. And then we're going to control how we do replication using the dependencies so we can still achieve causal consistency over top of this scalable partitioned base. So as it turns out, for a lot of the situations that we think about, single key get operations are just not enough. So if we return to the example where I remove my boss from my friends list and then say I want a new job, even if we replicate these things in the correct order, it turns out my boss can see my new status. So I'll show this with an example. So here we have a remote data center in the middle that my boss is accessing. And here's my boss, my advisor, and the web server that is producing his pages. So my operations have not shown up in his data center yet, and his web server goes out and gets my friends list. It gets the friends list that includes him as one of my friends. Then both of my operations show up in the correct causal order. And then the web server goes out and gets my status, and the status says, I want a new job. This is exactly what I didn't want to happen. Now you might think, oh, maybe you're getting these keys in the wrong order, but let's extend our example a little bit. So let's say I revert my status to, yay, I'm in Portugal, and I revert my friends list to include my boss again. So now the web server, before these two new operations show up, can go out and get the status that says I want a new job. And then both operations show up in the correct order, and it goes out and gets a friends list that includes my boss. So in short, there's no canonical ordering of these keys. Instead, what we need are get transactions. So what get transactions do is they're going to give you a consistent view of multiple keys, and they're going to give you this consistent view spread across many servers in the system. So it's not confined to a single machine. And I don't have time to go over the details of how we do this, but I encourage you to check out the paper or talk to me afterward to find out. So some of the other properties of these get transactions are, one, that they're going to take at most 2 parallel rounds of get operations in the local area to complete. And we do them without any locks and without any blocking. And these two properties are really important because they allow us to continue to guarantee low latency, even though we're giving you a consistent view of multiple keys spread across many servers. So let's return to our example and see how get transactions help us out. So let's just take a look at all of the possible combinations that the web server for my advisor could get. You don't really have to look at them all, but I want you to notice that there's never the combination where the friends list includes my boss and the status says I want a new job. So we avoided what we wanted to avoid. So on our system so far, we have these ALPS properties, and we have causal plus consistency, and we can even layer get transactions on top of it, but there's an issue here, and that's that we can have many dependencies in the system. And each of these dependencies requires metadata, and it also requires us to do these verification operations, these dependency checks. So what we really want to do is reduce both of these. So we have a couple techniques for those. These include using the concept of nearest dependencies and a couple techniques for garbage collecting unnecessary dependencies. So first off, where did all these dependencies come from? Well, they grow with client lifetime. So here's an example. So let's say I put something, and I put something, I put something, and then I get a couple things. I depend on each of those previous values as well as all of the values they depended on. So you can see this can quickly get quite out of hand. So what I can do is I can use the concept of nearest dependencies to reduce what I need in this system. So nearest dependencies, they're shown in green here. They're the dependencies that transitively capture all of our ordering constraints. So anything that is not a nearest dependency is depended on by a nearest dependency. And there's one nice property of these, and that is that even if there are a large number of dependencies, there's still a very small number of dependencies. So what do these nearest dependencies buy us? Well, these are the only things we actually need to check when we're replicating. We know that if we're after the nearest dependencies, we're also after all of the non-nearest dependencies as well, because they transitively capture our ordering constraints. So in our COP system, which is what we call the system we don't have any get transactions, this is all we need. We only need nearest dependencies. And anything that's not nearest, we just drop immediately. And this results in a very, very small amount of metadata in that system. And in our COPS GT system, which is what we call the system when we do have get transactions, here we have to track the non-nearest dependencies for transactional correctness, but we do not have to check them. We still only have to do the depth checks on the very small number of nearest dependencies. So I don't have time to go over it. We have a couple techniques that, again, are in the paper or you can chat with me about how to garbage collect dependencies so that we don't end up with lots and lots of metadata in the COPS GT system. So just to summarize these extensions to COPS, we have these get transactions that are going to give us a consistent view of multiple keys and do so while still guaranteeing low latency. And we just talked about nearest dependencies that really allow us to drastically reduce the cost of having this explicit metadata and having to check it. So when we evaluated our system, we wanted to answer 3 key questions. 1, what is the overhead of supporting these get transactions? 2, how well does this compare to our previous causal systems? And 3, how well does the system scale up? So to find out, we ran some experiments. And so our experiments, we have a local data center with n servers in it and n client machines. Each of these n client machines runs many threads of execution to fully load our servers in the local data center. And we also have a remote data center where we're replicating everything too, and this also has n servers. So when I talk about something with n equals 16 servers, 48 machines in the experiment. So let's take a look at our first question. What's the overhead of supporting these get transactions? So we'll take a look at this for a very simple workload that only has write operations, only puts, for n equals 4 servers in each data center. So on the y-axis here, I have throughput in thousands of puts per second. And on the x-axis, this is logarithmic. This has the average inter-operation delay. And so the way that you should interpret this is that when we're on the left here, this is like our system being fully loaded by a relatively small number of people, each tweeting 1,000 times a second. And when we're on the far right of the graph, this is like the system being fully loaded by a much larger number of people, each tweeting about once a second. So let's take a look at the results for our normal system COPS. You see there's a minimum latency we can support, and then we quickly ramp up to our full throughput. So now let's take a look at the results for our system with get transactions. So you see something very different here. There's a much higher minimum latency that we can support, and it takes quite a while for throughput to ramp up. So what's going on here? Well, when interoperation delay is low, each client is doing many operations every second. Each operation depends on the previous operation, so we end up with a very large number of dependencies in the system. In fact, we have thousands of dependencies over here. But if we take a look at the other side of the graph, when our write rate is relatively low, if you call tweeting once a second low, the overhead of COPS GT is actually pretty minimal. And this is great because this is what we expect. This is the workload we expect. So I don't have time to go over it here, but in the paper we do a much more detailed sensitivity analysis where we look at lots of different workloads with different read-write ratios and different numbers of people interacting in different ways. And I can just summarize the results for you. And it was similar to what we just saw. If we have a pathological workload, we can get a very large number of dependencies in the system. And our throughput for COPS GT is much lower. But when we look at workloads that we expect to see, we see that there's pretty much no overhead for having COPS GT, for having those get transactions. So now let's take a look at our second question. What's the overhead of the system compared to those previous log-based approaches? So if you take COPS and you get rid of dependencies, you actually get something that looks a lot like a log-based approach, especially when you think about the one server per data center case, which is what these log systems were designed for. So we took a look at this for a bunch of different workloads, and I have this graph here. I don't really want you to understand it. I just want you to believe that we did the analysis. So I'll quickly summarize it for you. So a COPS system and the log system, they both achieve very similar throughput. And this is for two key reasons. One, because we're only tracking nearest dependencies, we end up with a very small amount of metadata in our system. And two, because we only have one server in each data center, instead of these dependency check operations being expensive RPCs, they're just cheap local function calls. So let's take a look at our last question. How well does our system scale out? So on the y-axis, I have throughput, and this is logarithmic, so it keeps doubling. On the x-axis, I have a couple of different setups. And so I'll show you the results for the expected workload, though we have the other workloads in the paper too. So if it's the expected workload, we see that COPS GT is competitive with COPS and log. But really, how well do these systems scale out? So what happens when we double the number of servers? Well, we see that our throughput almost doubles. What happens when we double the number of servers again? So now we have 4 servers in each data center. Again, it almost doubles. And for 8 and 16 as well. So this is exciting, so we can continue to add capacity and throughput to our system by adding more servers to each data center. So in conclusion, today I presented our COPS system that is the first to achieve the ALPS properties and causal plus consistency. In addition, I presented our COPS GT system, which adds get transactions while maintaining our low latency requirement. To provide these properties, we introduced some novel techniques. These included the use of explicit dependencies that track causality between keys stored on different servers, and then explicitly verifying these dependencies as keys are replicated across data centers to ensure that they're only exposed in a causally consistent manner. Further, we introduced several optimizations that reduce the amount of metadata in the system and the number of dependency checks that we require so that we can provide these properties in an efficient manner. And finally, in our evaluation, we showed that for expected workloads, both COPS and COPS GT achieve high throughput and scale out.
Okay.
So I'm Abulabda from Cornell. So I'm actually a bit confused about how you achieve partition tolerance. If my operations are going to block until a server that has the dependency that I depend on responds back to me, I can talk to a data center, perform an operation, that data center gets partitioned away, I talk to another data center, but that data center didn't see any of the operations in which I depend on, and so I'm going to block. So how do I tolerate partitions?
Sure. So I think the question, if I can paraphrase the question, is that you have multiple data centers. It's possible that you depend on something that's being replicated from one data center that gets partitioned away, and then your updates aren't going to show up to a third data center until these updates are propagated from the now partitioned data center. Is that correct?
Yeah, and I'm blocking meanwhile.
Yeah, so you're not blocking anywhere. These operations won't show up right away. Causal consistency doesn't say, I see things right away. It's not strong consistency like that.
Yeah.
You'll still get to see consistent values. They just won't be super up to date.
I'll take it offline.
Hello, Meysam Yavande from Yahoo Research. Let's put detailed implementations and what you're setting aside. From an abstract point of view, I see lots of similarities between your model and snapshot isolation. First, both of you maintain multiple versions of data. Second, both of you talk about snapshots. And third, both of you try to detect and avoid write-write conflicts. I wonder about the differences.
Are you asking me the difference between this and what Jin Yang just talked about, PSI, or just snapshot isolation in general?
In general.
So in general, snapshot isolation is sort of a database property. So it's a stronger consistency than what you get. With snapshot isolation, you can do these transactions that have reads and writes and things like that. We don't have that in our system. What we have in our system is we're guaranteeing you low latency. Things will always complete right away, very quickly, no matter what.
But look, let's look at it as an abstract, from abstract point of view. I want to compare causal plus from an abstract point of view to a snapshot isolation. So
this is sort of tricky. So in the last talk, Jin Yang had this sort of spectrum of consistency models. What she was showing you was sort of more from the database side, where you have these transactions that involve multiple keys at the same time and lots of different updates and multiple operations and things like that. And we're more from like the sort of shared memory side or something like that, where all of these things involve one operation at a time. So how exactly they interact, it's like a very complex graph of how these consistency models interact. I would say that snapshot isolation is definitely a stronger property than what we provide, but we do so with better performance characteristics.
when you talk about write-write conflicts, write-write conflict makes sense if you have write conflicts between two transactions. You didn't call it transactions, but I guess in the paper you call it context or something like that. But you give it a different name, but it still is kind of context or it's kind of transactions. So
we only have read transactions. You can only read multiple values in a transaction together.
So when you talk about write-write conflicts, is between what and
write-write
what?
conflicts. So yeah, we can have write-write conflicts in our system, and we have to use either the last read or wins rule, or we have to use some sort of application-specific function that's going to resolve these conflicts for
But
us.
to have write-write conflicts, you first need to have...
I think we need to take this offline and carry on with the next question.
Marcos Aguilar, Microsoft Research Silicon Valley. So you made a case that gets are not enough, therefore you need get transactions. And
Yes.
the previous person was asking about other type of transactions. So you could also make the argument that puts are not enough and you need put transactions. In fact, you need more general transactions. And now you mentioned that you had the more perspective of a shared memory system, but there you have transactional memory as well. And so I'm wondering, like, without general transactions, isn't that the same thing as trying to go to war with rocks and stones when you have machine guns available with general transactions?
So I would agree with the first half of what you said and strongly disagree with the second half. So I think put transactions are important, and it's something that I'm thinking about. So what else did you say? General transactions. So I mean, my view of your work in the previous paper and this work is they're sort of complementary approaches. Like, we really want to have low latency. We say operations must be really, really fast. In your work, you say, we have to have these transactions. We have to avoid write-write conflicts. I think there's places for both of these, and I think that ultimately you'd probably have some sort of system that would join the two, but I don't think this is like using rocks. This is using something that you know is going to be really fast. I'm never going to have to do that slow 2PC across the wide area.
Okay, can we get the last two questions very short? Mark, is it a question?
A comment and a question.
Can we have the question?
Mark Shapiro, India. So the comment is, I think your causal plus property is much too strong. You can get exactly the same results with something a lot simpler, but we can take that offline. The question is, you said that explicit dependency tracking is novel. It's been around for a long time.
No.
It's been beaten to death.
Okay, sorry. I didn't mean to say that explicit dependency tracking itself is a novel technique.
Anyway, let me go
Doing
on.
this
Let
in
me go to the
conjunction
question.
With the decentralized replication
So, Mark, a very quick
is a
question.
new technique.
So the question is, vector clocks were invented because explicit dependency tracking is complicated and slow, and so why, I'm really puzzled, why didn't you just use vector clocks?
So we don't use vector clocks because we're talking about really big systems, and when we have this really big system, like let's say I have 1,000 nodes
Yeah,
in my
but they're
system,
compressed
then I'm
versions of
going
vector
to have a
clocks.
vector clock that has 1,000 entries in it, right? So this is going to be huge, and compared to the sort of small amount of metadata that we're propagating around normally,
That's been beaten to
1,000
death as well.
Okay, let's go for the last. Is it quick?
Yeah, real quick. Where is the metadata stored actually, like physically?
metadata, it's physically stored both on servers and in the client library.
On the servers, like where? In memory or? So my question is actually, how do you deal with like corruption of metadata or failures on the side?
So failures inside a data center, we sort of looked at this like, this is not where our main contribution is, and we took, there's existing techniques like chain replication and things like this that give you strong consistency, that give you this fault tolerance inside these data centers. We said, we'll just build on top of that. That's not where our contribution is.
Okay.
I mean, in terms of like dealing with, I don't know, bit flips or something, you probably want checksums in your system. I think Amazon came out with like, we really want that. This really screwed things up a while ago, so yeah.
Thanks.